Welcome to Unit 4, Lesson 4, Equations and Graphs of Polynomial Functions. Now that we have all this background information about polynomial functions, what we're going to do today is learn how to graph them. And once we are ready to do that, we have something called the multiplicity. And when we're talking about the multiplicity, we're talking about the zeros of the graph, or the x-intercepts. So the multiplicity of a graph is the number of times a zero of a polynomial function occurs. The shape of the graph of a function close to zero depends on it, and it's also known as the order of the function. So our general formula for that is x minus a to the power of k, or you can sometimes also see it as m for multiplicity. If k is odd, the graph crosses at x equals a, so here it would be odd. If k is even, the graph just touches at x equals a and changes direction. So here is an example of an even multiplicity where you can see it just goes up to 0, touches it, and then continues back on in the other direction. In this graph, zero multiplicity of 3, you can't see, but the graph is kind of going up and down along the lines there, and it's crossing at that x-axis. For us to graph a polynomial function, we need a bunch of information from the function before we can begin. We need to know the intercepts. That comes from finding your factors. We need to know the end behavior, so you need to know some of the characteristics of the function that you're looking at depending on the exponent, and kind of make a decision which quadrant should it be beginning and ending in. What is the constant term? That will tell us our y-intercept. The degree of the function will tell us the shape of our graph, and then the sign of the leading coefficient will determine that end behavior and show us which direction our graph is supposed to be heading. So we have this example, this polynomial. It's already been factored for us. We have zeros at x plus 1, 2x minus 1, and x minus 3. Now we have intercepts where these x's equal 0. So we have one here at -1, one at positive 1/2, and one at positive 3. Then we can plug in x equals 0 to find the y-intercept. So when x equals 0, what is y? So anywhere there's an x in your function, just put a 0 in there, solve for it, and we come out with a y-intercept of positive 3. So you can also draw that on there. Now the in-betweenies between these points doesn't really matter too much as long as you have the correct shape and the direction of the graph is reflective of the information that you've gotten from the function. So you can see in this one, we have a polynomial with a degree of 3. So we know it's going to be decreasing in the third quadrant and increasing in the first quadrant. It's a positive value for our leading coefficient. And we found all those other informations like intercepts and that direction to be able to determine what this graph would look like. So all I did to plot this, I found the 4 points that I was given. Where does it cross the y, and where are the places that it crosses the x? And then I used my end behavior, decreasing in this one, increasing in this one, and then just connected these lines. And that is how you graph a polynomial. I apologize, I probably should have given you just a blank Cartesian plane with just x and y axis here, but I didn't have the foresight to do that. So you can see here on my example graphs, for example, on this one, the maximum is at positive 32, and the y-intercept is at 0 and approximately 16. So I just graphed that out, but really, if you were drawing it on its own coordinate plane, it would probably look something like this, really tall and skinny, like this and like this, just increasing and decreasing very quickly. So as long as the general shape is correct, I'm fine with that, as long as you understand what the graph is supposed to look like. Don't forget to do these ones. You would have had to factor out your zeros and check the multiplicity to see what's going on at each of those points. So notice here we have a degree 3, but we have 2 intercepts. Okay, the graph of the shape of the graph has changed. It's increasing in quadrant 2 and decreasing in quadrant 4 because we have that negative symbol there. So all of these things are things to be aware of. Here in example A, we have a positive sign, so it's going down in 3 and up in 1. Here in C, we have a negative sign, so it's going to be going up in 2 and down in 4 instead. And the exact same thing here, you want to factor it out and find the zeros to be able to solve for this equation. Again, in example D, the point 0, 24, it's a bit off the graph, but just plot it as such to give the general shape, and you will be successful in plotting those graphs. I recommend using the app called Mathway and picking algebra. And you can just enter in the polynomials that you're given, and it will give you a nice plot of the graph, so you can kind of get an idea of correlating the information I've given you so far with what the graph is supposed to look like. Now again, we want to just talk about the multiplicity, and the multiplicity becomes very important because it tells you how many times one of the factors is going to repeat itself. So in this question, I've given you the function. I haven't told you what A is, the multiplier, or the leading coefficient, but I've given you the zeros of the graph. And you can see we have 1, 2, 3 terms, so you know it's going to be x to the power of 3. And what you can do to figure out what A is just pick any point on the graph where x equals something and has a value and solve for that value. So of course here we've picked this point 1, negative 8. Negative 8 is our y value and positive 1 is our x value. And of course at the end we are able to solve for A and have our unknown. So you just took a coordinate there and solve for that coefficient A. Now for this graph, you might not know how the heck did she get that function. So I just wanted to show you how to get to the function at the very end and give us the exact equation for it. Now above this we solve for A. We know A equals 2, so you can plug that value into A there. And then all you have to do is just multiply all the factors together. So you can't do it all at once. It doesn't work that way. You need to do the FOIL method on 2 of them and then apply the distributive property to the third one once you've done that. So in this bracket here, we have x times x gives us x squared, plus 1x gives us 2x plus 1. And then in the second part here, we're going to multiply x by each term in the brackets and negative 2 by each term in the brackets to give us all these terms. The following step after that is to collect like terms. So 2x squared minus 2x squared. Notice there's no x squared in our resulting function because plus 2 minus 2 cancels each other out. Then the last step, once you've done all that, is to just multiply the 2 into each term inside the brackets, and this will give you our final function, p of x is equal to 2x cubed minus 6x minus 4. I should go back up to the top here and just mention A, of course, will be the coefficient or the multiplier to tell us how far our graph is going to stretch vertically. And if you're wondering where did I get these values, x plus 1, x plus 1, x minus 2, you need to look at the intercepts, the x-intercepts on your graph. This one is at negative 1, 0. And you might be saying, well, why do you have 2 of them? How come? It doesn't touch it twice. But you need to remember about the multiplicity here. That tells you how many times you're going to multiply it by. If m is even, the graph bounces, touches, and changes directions at x equals a. So here it comes up to the graph and then changes directions and goes down, but it does not cross the x-intercept. In that circumstance, we have a multiplicity of 2. For this one, the graph goes straight through the point and continues on across the x-axis. So here is our other 0, x minus 2. And then you just follow the steps that we talked about before to solve for the problem. You can also be given application questions for this type of problem. So you're given a cube. Bill is given a cube of ice. He's going to make a sculpture for Festival. And it's asking you, what is the function, the polynomial of the function? And then how much should he remove from each dimension to get this volume of 24 cubic feet? Method 1 is to use a graph, but method 2 seems a lot simpler, so we'll go with method 2. Now we have this function v of x, the volume of that cube is equal to those three sides multiplied by each other. And if we just plug in the value that we know, 24, that's our goal size, and then just solve for the function by multiplying through. So our resulting function we end up with is negative x cubed plus 12x squared minus 47x plus 60, and then at the end we're going to move the 24 over to this side by subtracting 24 from both sides, and then divide out the negative from the factors of the polynomial function. Now we want to find the factors that work for this function. So once we have this x cubed minus 12x squared plus 47x minus 36, we want to look at that constant term and figure out what are some possible factors of 36, which we've done previously: 1 and 36, 2 and 18, 3 and 12, 4, 9, and 6 by 6. Those are all possibles. Start with 1. It's the easiest spot to start at. So plug in x equals 1, see if there's a remainder at the end. There isn't, so we know that x minus 1 is a factor of that original polynomial that we're given. Once we know that that's a factor, we're going to divide the polynomial by it, and the remainder that you're left with is x minus 1 times x squared minus x plus 36. Now this function, if you look back at the terms for the 36, none of these plus or minus added together with each other will give you negative 11x if you're dealing with them in the pairs that make up positive 36 as multiplying factors. So therefore, in this circumstance, you have to use the quadratic formula, and you should be familiar with it already. But when we have our polynomial written out in the form ax squared, a of course is 1 here, minus plus bx, here it's negative 11, plus 36, or c. Okay, so they're outlined down here actually. A equals 1, b equals negative 11, and c equals 36. And then you just fill in the quadratic formula and solve for the possible values of x. This is sometimes a way to find out the other zeros of the function, but you get lucky in this circumstance because you end up with a root of negative 23, which doesn't have any real roots, and therefore the only real root of this function is x minus 1, or x is equal to 1, and therefore we know that Bill needs to remove 1 foot from each dimension to get the volume of 24 cubic feet. Beyond the notes, you have some practice questions that you can complete independently for tomorrow.